I'm Latha from Tata Consulting Engineers. I would like to start with an introduction of the energy scenario in India, with the evolution of control systems followed by Scada automation, our implementations and way forward. As a baseline, we started working towards electrification from long ago, and when measured in 2000, the world was supposed to be 78% electrified as per World Bank report. Now we are approximately around 91%, and we intend to completely electrify the world by 2030 as per Sustainability Development Goals. Coming to Sustainability Development Goals, electrification plays a very important role in promoting poverty, zero poverty, good health, economic growth, infrastructure development, industrial development and innovation in addition to climatic actions. I'm very proud to say that we have the first completely electrified village in our country, Madera in Gujarat, wherein all the 1,300 houses have been electrified. People are very happy here that they need not pay any electrical bills. In addition, they are able to give back to the grid also. Coming to the power plant installed capacity in India, right now we are at 416 gigawatts, wherein coal and lignite play a very important role, occupying 51%, followed by renewable sector with 125 gigawatts of generation capacity. With reference to renewable sources, solar power occupies a major share of 53%, generating 67.1 gigawatts of power, followed by wind power with 42.9 gigawatts. And this is the projection of the energy scenario of India as per IEA report. We were supposed to generate 50 gigawatts by 2020. We are at 2023, wherein we are generating 125 gigawatts. By 2030 and 2040, we need to, the projections are 207 and 622 gigawatts respectively. To achieve the solar targets by 2027, we need to generate 185 gigawatts, which could form 30% of the total power requirement in our country, followed by 40.5% in the year 2031-32. At TCE, we have engineered around 25 plus gigawatts of solar power plants, including support to pre-bid engineering, around I could say 40 gigawatts. We are into all type of solar power plants, whether it's ground mounted, floating, concentrated, solar rooftop, including battery energy storage systems. We support owners engineering, lenders review, EPC contractors and OEMs in feasibility studies, environmental impact studies, evaluation of technologies, design and detail engineering, project management and coordination, solar radiation data analysis, construction and commissioning support, and due diligence services. To give you a fair idea, this is a snapshot of the biggest solar, ground-mounted solar power plant in the world. It's the Badla Solar Power Park in Rajasthan, which generates 2,245 megawatts. TC was involved with Hero Futures for one portion of the plant, and we have a Tata Power Solar, which was involved in the engineering of the project too. This is a snapshot of Kankulam floating solar power plant in Kerala. This is again the largest in India, generating 101 megawatts of solar power. Currently it's generating 92 to 93 megawatts of power. These are a few more snapshots of the beautiful Kankulam solar floating plant. TC has a patent in floating solar plant design, wherein there is no practical limitation to the tilting angle of the solar panels. The panels could be tilted from 5 to 30 degrees depending on the design, and it is suitable for high and low water levels with maximum wind load withstanding capacity, and this innovative design uses the locally available material. The second application of solar is rooftop projects, wherein we have around 1100 megawatts of rooftop implemented in our country. The roof area could vary from 100 to 1200 square feet, generating 1400 to 14,000 units of electricity. The third application is the use of solar pumps in the field of agriculture from solar panel. The fourth, I think there was a slide yesterday regarding this application. It's referred to as a microgrid, wherein small islands or remote locations or some defense applications wherein some secrecy has to be maintained at remote locations, or some hospitals or isolated college campuses could have this facility. Here we have power resources and the consumers which are controlled by a microgrid controller within an electrical boundary. This most of you would be familiar. We started with the pneumatic control systems and now we are at open process automation. In power industry, starting from the power module generation to the distribution to the final consumer, almost everything is automated. That is what I would like to show in this picture. We have the generating station in the first part, and then the substation followed by transmission and distribution lines to individual consumers. There is a typical Scada control system which is very famous and commonly used for monitoring, control, data acquisition. The main, these features of Scada are self-explanatory, right? We know that Scada is flexible and a scalable system. This is a typical architecture of Scada automation system and a solar power plant. Here we have the strings or tracking system for the panels, the inverters generally connected in the form of a daisy chain, the weather monitoring systems and soiling stations, the switchgear, transformers connected to operating cum engineering stations. The switchyard also is connected to the common Scada for the solar power plant and switchyard, and through a firewall it's connected to the grid operator, which is a mandatory requirement, and a web client which is used for remote monitoring and control. Yeah, these are the standard features of Scada. In addition to the regular applications like high scan times, sequence of event recorders and alarms, we also have remote data through OPC UA, Secure File Transfer Protocol, FTP, and data transfer to State Load Dispatch Center and the National Load Dispatch Center. These are a few screenshots of the Scada graphics of switchgear, switchyard, inverter sections, and the control system configuration. Generally, the red color is used to indicate that there is a malfunction, and the green color indicates the healthy system. A few benefits of Scada, including edge computing and data analytics, ease of integration with third-party systems, and built-in security. Now coming to the case studies, we have implemented remote monitoring of our own assets. We have multiple solar plants and wind plants as a part of our ecosystem. We can have a fleet view which shows the entire set of solar plants to be monitored. the overview dashboard, plan monitoring, daily generation reports, preliminary analysis, forecast scheduling, and then a separate screen for wind is considered, and then the advanced analytics. All these interfaces are currently being communicated through OPC UA. This is a typical configuration of plant connectivity. We have the field sensors connected through the data logger to the Scada system, and then through a network PI node, through internet lease lines, through Pi server to the central control room. This is an integration overview. As most of you are aware, the solar system, the solar power plants are relatively new in the industry when compared to the thermal power plants or the gas-based power plants. Initially, we had the wind power plants, the Scada and the OEM data center. All these used to be proprietary like a black box. However, now the new wind plants and solar plants have the Scada, which is an open system, and we can extract data to our central control system using the Scada. This is a typical graphic screen wherein we can combine wind and solar plant data. Everything is available for monitoring. My second case is remote monitoring and analysis of EPC assets. Sometimes the owner will not like to maintain his own assets, so he employs EPCs for a period of say 10 years or 20 years to monitor and control and maintain his assets. This is a typical application wherein we have used AI and ML based analytics. The green portion shows the healthy assets, and the red portion shows the assets requiring maintenance or replacement. The graph here is the solar loss curve, and here we have collaborated with third party and in-house ITAP data logger for remote web-based SCADA monitoring too. These are three different cases and in three different plants. The third application of remote monitoring and control is that we have achieved remote control of breakers. For example, my plant could be somewhere in Tamil Nadu. In this specific case, we have controlled the breakers from our central control room in Mumbai. Coming to my second topic of advanced automation implemented, we have string monitoring boxes in a power plant. We have used wireless technology in this case. This is a classic example of weather monitoring system. Most of you might have seen weather monitoring systems mounted on top of the control rooms, right? This is basically, since we have an Ethernet limitation of 100 meters. In this particular case, since we have used wireless in combination with MQTT and cloud, we could keep the weather monitoring station anywhere in the plant. The third advanced automation application we have implemented is a lightning arrestor interface with Scada. In earlier days, we used to have analog meters for the lightning arresters with counters. People used to needed to go to the particular site and see whether the counter has increased the value. Solar plants cover a very huge area in terms of thousands to 10,000s of hectares. So it's very difficult for a person to go to each and every transformer or a lightning arrestor module and see the counting, right? So in this case, we have implemented a wireless lightning arrestor interface wherein the digital data is available on my Scada screen. With this, as soon as the lightning strikes, I get the information in my Scada system wherein it is time stamped, and this data will be useful even for insurance purposes. since my insurance person needs to know whether it is a man-made fault or a natural disaster at times. Further, this also helps in reviewing the equipment connected along the line and helps us in further improvements and maintenance. The fourth application is a mobile access of Scada. We can have display of all the features available in our Scada on our mobile phones. Coming to solar performance improvement, we have implemented tracker remote control, which is a game changer initiated in our plant. Hemant, can you play? I have a short snap to illustrate this. We have different modes. Yeah, this was a short clip of combination of wind monitoring system and the data from the Indian Meteorological Department, which was used to move the trackers. During rains, the tracker should be in stop position, which helps the rainwater to flow down so that there is optimum solar power generation. This is real-time monitoring of negative grounding of inverter, which is more happening in case of rainy seasons due to aging. We have introduced a safety fuse in this circuit and some amount of automation, wherein in case there is a negative grounding of the inverter, the fuse blows and we come to know in our Scada system. Based on the data available, the fuse could be replaced. This prevents the inverter from degradation also. One more important application is the development of the power plant controller, which is made in-house. Generally, we have a forecast given to the grid controller, the power plant load dispatch center. We'll have to tell them like we'll be generating for example 50 megawatts of power. So in case I've already forecasted the value, the grid operator will allow me only to vary the value by plus or minus 10%. Otherwise my plant will be liable for disconnection. This in a normal set point based system, there could be some losses like soiling losses, transformer losses, or some inverter problems and so on. The automated power plant controller system considers all these factors and gives a set point to the PPC and generates optimum power so that I don't lose anything. My generation will be maintained between 48 and 52 megawatts and I get more money also. There won't be much losses in the system. Earlier, before the implementation of PPC, there were a lot of disconnections happening in our plants. The last section is the predictive analytics implemented in our systems. Since we are running plants for the last 2 to 3 years, we have ample data available in our plants. This is compared with the currently available current data or the real-time data, and it is used to, it is analyzed with respect to the already available data, generates alerts or alarms and enables people to act on it. This is a solar loss prediction curve. Again, enabled mobility and enabled improved data availability. This plays a very important role in inverter and string performance analysis of the solar plants. We also have the global horizontal irradiation and generation prediction reports. We do have the generation prediction and the actual prediction and the deviation also, which helps us in improving further. This is the advanced analytics snapshot, wherein data of all the plants is available on my screen. We also have advanced analytics in the form of events like inverter trip or inverter malfunction, and the number of times the inverter is not working, and the forecasting and scheduling screens, daily generation screens, and so on. And coming to the solar rooftop estimates, I'm happy to say that with the help of a Google image, I could get a precise estimate generation of the solar power that can be generated from the system as well as the hardware components. There is a first state-of-the-network operating system center in India. The way forward, right now we have come up to this remote control center. The future could be having a global headquarters too. This is a summary of whatever I explained now. We have Scada, which is scalable with forecasting, scheduling capabilities, and provision for integrated solutions, advanced analytics with the help of OPC-UA, OSI, and Python with remote diagnostics capability. This is a recap of all the functions of a total remote monitoring control system. The future could be like centralized control of multiple plants. We could have master PPC controls from SLDC or Grid India, and with 5G we could have better speed, latency, multi-device connections, and unlimited data transfer. In fact, Ericsson is working on 7G right now. There could be a lot of developments in transformer, predictive analytics maintenance, soiling station advancements, IoT-based systems, and building integrated photovoltaics into the constructions, like providing glazing surfaces like windows, skylights, sun doors. We can also have solar roads to charge vehicles and for traffic control, and solar roofs. And we could also have solar textiles, wherein backpacks, tents, curtains, etc. could be used for charging mobiles and lighting. I would like to thank Tata Power Solar for the information provided, and this is a general disclosure. Thank you.